Good afternoon to all. Let us see the remaining preparations of haloalkanes which are left. Okay, Swarts reaction is left. Next is nothing but Finkelstein reaction is left. Before going into these two reactions, let us talk something about iodination as well as fluorination. So, iodination of hydrocarbons. Iodination of hydrocarbons. Iodination of hydrocarbons. Nothing but reaction of iodine with hydrocarbon. That is nothing but iodination. Let us consider a hydrocarbon in this way. CH4. It is a hydrocarbon. Okay, when we are reacting this with iodine, then it forms CH3I, methyl iodide plus hydrogen iodide gets produced. The products which got produced here, they will react again to form the reactants. Nothing but it is a reversible reaction. It is a reversible reaction. Reversible reaction. Okay. So, in order to stop the reaction of hydrogen iodide with methyl iodide, okay, we will add hydroiodic acid, HiO3. When we are adding hydroiodic acid, this hydroiodic acid, it will react with the hydrogen iodide and convert that into iodine. Okay, nothing but it will make the hydrogen iodide to undergo oxidation. So it is acting as an oxidizing agent. It makes the hydrogen iodide to undergo oxidation. See the reaction. Hydrogen iodide which got produced here, it will react with iodic acid, HiO3, to form iodine plus H2. So here HiO3, if you see, it is acting as an oxidizing agent. So it is making the hydrogen iodide to undergo oxidation. It acts as an oxidizing agent. So there will not be any hydrogen iodide left to make the reversible reaction. So keep this in mind. So whenever we are reacting iodine with a hydrocarbon, we will add an oxidizing agent, HiO3, or we can also add HNO3 as an oxidizing agent. These two will act as oxidizing agents to convert hydrogen iodide into iodine, so that the reversible reaction will not get proceeded. Okay, please take this. Now let us see about the fluorination of hydrocarbons. Fluorination of hydrocarbons. When pure fluorine is reacted with hydrocarbon, then the reaction will be explosive in nature. So, in order to avoid that, we consider dilute fluorine. We will react dilute fluorine with the hydrocarbon to produce alkyl fluorides. Okay, so with what we will dilute the pure fluorine means we can add either nitrogen or argon in order to dilute fluorine. So when we are diluting it, explosive reaction will not take place. Fluorine will be highly reactive in nature. So since it is highly reactive, explosive reaction will take place. Okay, nothing but the reaction will be exothermic in nature. More energy gets produced. Okay, reaction of fluorine with hydrocarbon is an explosive reaction, or it is an exothermic reaction. High amount of energy gets produced. So due to high amount of energy which gets produced, it will be explosive in nature. So in order to avoid that, we will dilute the fluorine. Okay, or there is an alternative method in order to prepare alkyl fluorides. We will see that also. Okay. So, you can write it is explosive in nature. Explosive in nature. We add nitrogen or argon to dilute pure fluorine. Okay. Now let us see the Swarts reaction as well as Finkelstein reaction. First, let us talk about Finkelstein reaction. Finkelstein reaction. Okay. So this Finkelstein reaction, it is used for the preparation of alkyl iodides. It is used for the preparation of alkyl iodides. We take the reactants as alkyl chloride or alkyl bromide. We react them with sodium iodide in presence of dry acetone, so that alkyl iodide will be produced. See the reaction. I am taking ethyl bromide or bromoethane. This one reaction with sodium iodide in presence of dry acetone. It will produce iodoethane. Iodoethane will get produced. Nothing but alkyl halides are getting produced. Along with this, sodium bromide will also get produced. See, the sodium bromide which got produced in this reaction, it will be soluble in the acetone. So that it will get precipitated out. The sodium bromide which got produced here, it will be insoluble in acetone which we are taking, so that it gets precipitated. Okay. So according to Rechart's principle, since there is decrease in the amount of product on the right hand side, the reaction will proceed in the forward direction. This is how Finkelstein reaction will take place. So here what you need to remember is nothing but Finkelstein reaction is used for the preparation of alkyl iodides. Here we use sodium iodide in presence of dry acetone. Okay. This is about Finkelstein reaction. The next reaction is nothing but Swarts reaction. The next reaction which we are going to see is nothing but Swarts reaction. This reaction, it is used for the preparation of alkyl fluorides. Okay. As I said before, when we are reacting fluorine with hydrocarbon directly, it will be an explosive reaction. So there is an alternative method in order to prepare alkyl fluorides. That is nothing but we will take alkyl chloride or alkyl bromide as the reactant. For example, CH3 Br you can consider. These one we react these with metal fluorides. Like for example, we can take silver fluoride, or we can also consider cobalt fluoride, COFT, or we can also consider stibine fluoride, or we can consider mercurous fluoride. Okay, so anyone can be considered. Okay, so we will react the alkyl bromide or alkyl fluoride with metal fluorides. With inorganic fluorides, we are reacting the alkyl bromide or alkyl chloride. So, for example, if we are taking silver fluoride, okay, this silver fluoride on reaction with methyl bromide, it will form methyl fluoride as the product, and silver bromide will be left. So, this is the preparation of alkyl fluorides from alkyl bromides or chlorides. This is nothing but Swarts reaction. You need to understand that Swarts reaction is used for the preparation of alkyl fluorides. In the same way, Finkelstein reaction is used for the preparation of alkyl iodides. You need to remember these things. In the objective questions, they will ask. Okay, Swarts reaction is used for the preparation of, or Finkelstein reaction is used for the preparation of, or in which reaction metal fluorides are used. So these type of questions can be asked. Please remember these things. Please note down. Now the next topic is nothing but physical properties of haloalkanes and haloarenes. We have completed the preparations of haloalkanes and haloarenes. The next topic that we are going to see is nothing but physical properties of haloalkanes and haloarenes. Let us start. Physical properties. Let us start about physical properties. In this, the first one is nothing but melting and boiling points. Melting and boiling points. So when we compare the melting and boiling points of haloalkanes and haloarenes with their corresponding hydrocarbons, okay, haloalkanes and haloarenes will be having high melting and boiling points. Okay. Let us first talk about haloalkanes. Let us consider different haloalkanes. Okay. CH3F, CH3Br, CH3Cl, CH3Br, CH3I. Okay, so these are the different haloalkanes: methyl fluoride, methyl chloride, methyl bromide, methyl iodide. Okay, now as the size of the halogen atom increases, okay, boiling point will also increase. See here, methyl fluoride, methyl chloride, methyl bromide, methyl iodide. So we know that among the halogens, fluorine, chlorine, bromine, iodine is large in size. Since iodine is large in size, okay, van der Waals force of attraction between methyl iodides will also be more. If it is more energy is required to convert them into vapor state. That is why methyl iodide will be having more boiling point when compared with the remaining things. The order will be in this way: methyl fluoride is less than, methyl chloride is less than, methyl bromide is less than, methyl iodide. Okay, so here same alkyl group but different halogens. Okay. The next thing, when the number of halogens increase, the boiling point will also increase. For example, CH3Cl, CH2Cl2, CHCl2. Okay, so if you see these, the halogens are increasing. When the number of halogens increase, the boiling point will also increase. Okay, CH3Cl will have low boiling point when compared with CH2Cl2. It will have low boiling point when compared with CHCl3. Okay, these are boiling point orders. Boiling point orders. The same thing here also. Okay. Let us consider isomers of haloalkanes. Okay, for example, CH3, CH2, 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 Cl. Okay, so this is nothing but chlorobutane. Okay, the isomer of this, if you see, CH3, CH2, CH, Cl, CH. This is the isomer of this chlorobutane. This is one chlorobutane, this is two chlorobutane. Let us see one more isomer, that is nothing but CH3, CH3Cl. This is the next isomer. Okay. So this is nothing but tertiary butyl chloride also we can say. Tertiary butyl chloride. Or 2-chloro-2-methyl propane also we can call. 2-chloro-2-methyl propane. Okay. So these are the isomers. Isomers means what? What is the meaning of isomers? They will have the same molecular formula. Okay. So they will have the same, isomers are nothing but which are having the same molecular formula but they differ in their properties. We generally call them as isomers. You can observe the molecular formulas in these three things. They are having the same molecular formula. Okay. So this is 1-chlorobutane, 2-chlorobutane, tertiary butyl chloride, or we can make it as the name as 2-chloro-2-methyl propane. So here if you see the boiling point of these isomeric haloalkanes, okay, generally it depends on the branching or the surface area. Okay, as the surface area increases, van der Waals forces between the molecules will also increase. Okay, if the van der Waals forces increases, boiling point will also increase. Okay, boiling point, it depends on the surface area. As the surface area increases, boiling point will also increase. Okay, the molecules which are having low branching, they will have less surface area. Okay, so in them the boiling point will be less. Nothing but among these three, this third one, it has more branching when compared with the first and the second. Since branching is more, surface area will be less. If surface area is less, force of attraction between the molecules will be less. That is why tertiary butyl chloride will have low boiling point when compared with 2-chlorobutane and 1-chlorobutane. And when we compare 1-chlorobutane and 2-chlorobutane, 1-chlorobutane will have high boiling point. So the order will be 3 is less than 2, 2 is less than 5. So remember one thing, as the surface area increases, boiling point will also increase. When surface area increases, when there is less branching, surface area will be more. As the branching increases, surface area will be less. Okay? Please take these things. The next thing is nothing but when there is increase in the alkyl chain, then also the boiling point of the alkyl halides will increase. For example, CH3Cl, CH3CH2Cl, CH3CH2CH2Cl. If we observe these alkyl halides, okay, there is increase in the alkyl chain. The number of carbons are increasing now. Nothing but the length of alkyl chain will also increase. If there is increase in the alkyl chain, surface area will increase. If that increases, force of attraction between the alkyl halides will increase. So boiling point will increase. Okay. So among these three compounds, we know that the third will have high boiling point. Next second, next first. So the order will be 3 is greater than 2, 2 is greater than 1. This is nothing but boiling point order. Okay. So this is something about boiling points of haloalkanes. Next we will be seeing the boiling points with respect to haloarenes, boiling and melting points of haloarenes. Please take it. So whatever we have discussed regarding the boiling points and melting points of haloalkanes, the same is applicable for haloarenes also. Okay. Haloarenes. Okay. Let us take the examples. Fluorobenzene, chlorobenzene, bromobenzene. Next is nothing but iodobenzene. Okay. 1, 2, 3, 4. So here if you see benzene, there is no change in the arene group, but there is change in the halogen. Okay, there is change in the halogen. There is no change in the arene group. Okay, fluorobenzene, chlorobenzene, bromobenzene, iodobenzene. Okay, as the size of the halogen increases, we know that force of attraction between the molecules will also increase. Nothing but van der Waals forces will increase. So, more energy will be required to convert them into vapor state. So, the boiling point of iodobenzene will be more than bromobenzene, then chlorobenzene, then fluorobenzene. The order will be 4 is greater than 3, 3 is greater than 2, 2 is greater than 1. This will be the order. So, as the size of the halogen increases, the boiling point will also increase. Keep this in mind. Now let us consider dihaloarenes. Okay, let us consider dihaloarenes. So dihaloarenes means 2 halogens will be present. Let us consider dichlorobenzene. Dichlorobenzene. This is 1,2 dichlorobenzene, or we can call it as orthochlorobenzene also we can call it as 1,2 dichlorobenzene. Next 1,3 dichlorobenzene. Next 1,4 dichlorobenzene. Okay, so among these 3 types of dichlorobenzenes, see 1,4 dichlorobenzene, it will be symmetrical in nature. Okay, it is symmetrical in nature. Since 1,4 dichlorobenzene is symmetrical in nature, the molecules will be close to each other. When they are close to each other, the force of attraction will be more. So in that case, when we want to convert that into a liquid, okay, then the melting point will be more. Okay, so among these 3 things, 1,4 dichlorobenzene will have high melting point. The reason is nothing but 1,4 dichlorobenzene is symmetrical in nature. Since it is symmetrical in nature, it can fit in the crystal in a proper way. Nothing but the molecules will be close to each other. When they are close to each other, force of attraction will be more. Okay, so more energy is required to convert that into liquid state. That is why 1,4 dichlorobenzene will have high melting point among these 3. And when we talk about boiling points, almost all the 3 will have same boiling point. So that's about boiling point. So when we talk about melting points, this is the third one, second and first. So when we talk about the melting points, okay, 1,4 dichlorobenzene will have high melting point. Next will be 1, next will be, please take this order. The next physical property is nothing but density. Density of alkyl halides. Okay. As the size of the halogen increases, density will also increase. For example, methyl chloride, methyl bromide, methyl iodide. Here you see halogen size is increasing when you move from left to right. So methyl iodide will have more density when compared with methyl bromide or methyl chloride. So the order will be in this way. This is less than this is less than this. Okay. And one more thing is nothing but as the number of halogens increase, then the density will also increase. For example, example, CH4, CH3Cl, CH2Cl2, CHCl. See, if you see from left to right, the number of halogens are increasing. As the number of halogens increase, density will also increase. So CHCl3, it will have more density when compared with CH2Cl2, CH3Cl or CH4. Okay, so the order of density will be in this way. It will be in this way. Nothing but as the number of halogens increase, density will increase. As the size of the halogen increase, density will increase. Remember these things. Please take it. The next physical property is nothing but dipole moment. Dipole moment. Okay. So let us take an example to understand this. Methyl fluoride, methyl chloride, methyl bromide, methyl iodide. Okay. Remember one thing, as the electronegativity of the halogen decreases, dipole moment will also decrease. Okay. So among these four, which will have the least dipole moment means methyl iodide. Methyl iodide will have the least dipole moment value, because electronegativity of iodine is less when compared with bromine, chlorine or fluorine. Since electronegativity is less for iodine, dipole moment will also be low for methyl iodide. Okay, but when we see methyl fluoride and methyl chloride, although fluorine is more electronegative than chlorine, the dipole moment of methyl chloride will be more when compared with methyl fluoride. The reason is nothing but dipole moment not only depends on the charge, but it also depends on the distance between the ions also. Okay, here if you see fluorine, since fluorine is small in size, bond length will be less. In case of chlorine, since it is large in size, bond length between carbon and chlorine will be more. So dipole moment, it depends not only on the charge but also the distance between the ions. Okay, since fluorine is small in size, the bond length between carbon and fluorine will be low. So that is why the dipole moment of methyl fluoride, it will be low when compared with methyl chloride. So if you see the order, 4 is less than 3, 3 is less than 1 is less than, this will be the order, dipole moment order. Now let us see dipole moment in haloarenes. Let us consider dihaloarenes. Okay, I am considering dichlorobenzene. Dichlorobenzene. I am considering the isomers of dichlorobenzene, orthodichlorobenzene, metadichlorobenzene, paradichlorobenzene. Paradichlorobenzene. Okay, this is metadichlorobenzene, this is paradichlorobenzene. Among these three dichlorobenzenes, the least dipole moment value will be for paradichlorobenzene. The reason is nothing but it is symmetrical in nature. If you see the bond moments, see carbon, chlorine. Since chlorine is more electronegative than carbon, the bond moment it will be towards chlorine in this way. In the same way here it will be in this. Bond moment will be towards chlorine. Okay, so if you see the two bond moments, they are opposite to each other. Since they are opposite to each other, they will cancel. So the resultant dipole moment value will be 0. Okay, since paradichlorobenzene is symmetrical in nature, the individual bond moments of carbon and chlorine, they will get cancelled. They are opposite to each other, so they will get cancelled. So the resultant dipole moment value will be 0. So in case of orthodichlorobenzene and metadichlorobenzene, we need to consider the bond angle between the two chlorine atoms. Okay, the one which is having low bond angle between the two chlorine atoms. Okay, it will have high dipole moment value. Remember this thing. So the order will be in this way. Para, it will be greater than ortho is greater than meta. Please take this. The next physical property which we are going to see is nothing but solubility. Okay, let us talk something about this solubility. So generally we know that if you see haloalkanes, they are polar in nature. Haloalkanes are polar in nature. Water is also polar in nature. Although haloalkanes are polar in nature, they are generally insoluble in water. Why haloalkanes, although polar, why they are insoluble in water? Okay, although haloalkanes are polar in nature, they are insoluble in water. They are insoluble in water. The reason is nothing but so when we are adding a haloalkane to water, so the new bond which gets produced between haloalkane and water molecule. Okay, so when a new bond gets produced between haloalkane and water molecule, energy gets released. That energy which gets produced is not sufficient to break the hydrogen bonds which are present between water molecules. Okay, that is why haloalkanes, although polar, they are insoluble in water. Once again I am revising. Okay, please listen carefully. Haloalkanes are polar in nature. Water is also polar in nature. Actually, haloalkanes, they should get soluble in water because they are of same nature. But haloalkanes are insoluble in water. The reason is nothing but the energy that gets released when a new bond is formed between haloalkane and water is not sufficient to break the hydrogen bonds which are present between water molecules. Okay, so that is why haloalkanes will be insoluble in water. Okay, simple thing. So this is about solubility. So these are the physical properties of haloalkanes and haloarenes. So what are the physical properties which we have discussed? We have discussed about melting and boiling points. Okay, and then we have discussed about density. We have discussed about dipole moment. We have discussed about solubility. Okay, these are the things. Okay, that's all about physical properties. In the next class, we will be seeing about nucleophilic substitution reactions. Thank you all.